So, hi everyone, and thank you all for coming. And today I'm going to show you, to guide you through some work that I've done on an open source project this summer, which was part of our Google Summer of Code project. And this was mainly for me kind of trying to get into low-level stuff and systems programming, mainly operating systems and the kernel. And I would like to introduce you first to CRIU, and then get into the details of the implementation that I had for CRIU for this project, which was initially designed for students, but since recently it's open for anyone who has enough time, and I had a lot of time this summer. And let me just first ask, does anyone know what CRIU is, or you ever heard of it, or saw it, or like just a hand or something? No? Nada. You know, because, yeah, okay. Okay. So this is going to take part, as I mentioned, in two parts, and one is just how CRIU works, and the other one is me implementing an Arm64 upcoming feature in CRIU so that it doesn't break when it does what I'm about to show that it is supposed to do. CRIU, short for checkpoint and restore in user space. And like the gist of it is it stops the process, takes it down from memory, and puts it back in another machine, and it all works fine. Like it never changed its environment. And this project was started by Virtuoso. Maybe you've heard about it, like the engineers from Virtuoso. And if you see the Mad Russians quoted here, this is actually a direct quote from the patch linked down here, which you can see was a fun discussion. Some guy in the patch that was replying to it didn't really believe that this could be as successful as it is today. And also it's worth mentioning that it's based on a repo that is from this person, Tejun Hell, or I don't know if I pronounced that right, which is called Parasite Thread, and that's also linked down below. So it deserves its credit because CRIU wouldn't exist if it weren't for that. And this is an old repo based on kernel 3 point something. Since I mentioned Virtuoso, I just want to mention that they also have a couple of more open source products, so to speak, or projects. One is this OpenVZ, which is a hypervisor, and the other one is VZ Linux, which is a distro that runs on their own infra better than some stock stuff, I assume. One other thing worth mentioning is, so I said the process is being frozen and it's being snapshotted and restored to another machine. This is in container worlds called live migration, and it can be served different purposes such as load balancing or maybe just other changing the workload or scheduling different types of workloads. And what I wanted to mention, it's important to know that CRIU itself does not support iterative migration. And by iterative, in this context, it's meant that it does memory dumps all the way up until the freezing of the process takes place. And then so that the memory dumps that it has to do while the process is still running is minimal and the downtime is minimal. So this is kind of a performance aspect to it. And one more thing worth is another link, which is the credits for other people that have contributed to this. I consider CRIU to be a piece of the art when it comes to software and understanding the kernel and the operating system. And yeah, so it's just good to always give credit to people who built this. So I mentioned that it's short for checkpoint and restore in user space. And you may ask, why not in kernel? And this actually was a thing in OpenVZ6, where there was a huge code patch for the kernel that existed, and it was very expensive to maintain this patch while bringing in changes from the upstream, and that took engineering time, and also getting stuff back in the upstream was not easy. So this became a problem, and at some point CRIU was born. And yeah, again, reminder that the main reason was live migration of containers. And this migration typically involves two transfers. One is these memory dumps, which are specific .emg files per CRIU's spec, and then the containers file system mounts. That is all transferred. The container is recreated, mounts reattached, and then CRIU does its magic that restores all the stuff from the image files. It can also be useful for snapshots, or some people do it to do forensics on malware, for example. Like you can do these snapshots in different points in time or different situations and analyze the memory dumps. And I didn't put this on the slide, but since the next point is accelerated startup of processes and containers, I've seen some articles that, for example, people would speed up JVM startup time significantly using CRIU, just restoring it from a dump. And yeah, CRIU also restores TCP connections and many more things. I'll get to that. And you can also, like, there's a link here. There's some really weird scenarios. If anyone's interested, I mean, you can get the slides later, but there's some really interesting usage scenarios for CRIU that you might not anticipate. Okay, so when I first started working with CRIU, I was like, okay, so we just pull down stuff from memory, bring stuff back in memory, and like the process resumes, you just store the registers and the program counter, right? But then, because I had 3 mentors for this project, and that was a blessing, I can say. There was like VMAs, okay, registers, open file descriptors, thread local storage, sockets, network devices, virtual interfaces, DTYs, and the process could have been in the middle of signal handling, which can complicate things, add more logic, C groups, task attributes, which contain some credentials, R limits, namespaces, and so on. And when it comes to namespaces, just a small reminder, this can be used as reference points even afterwards, that they are primitives upon which isolation for containers is built upon. And you can look up, there's a nice blog about write your containers from scratch, something like that, and then you learn how to use the namespaces. And mount was one of the first namespaces to exist in the kernel. Then others were slowly added, and one thing note saying is that user namespace is they consider it a special namespace because you don't like the others on the outside. Let's say that you are UID 1000, you're outside UID 1000, you're inside UID 1000, but the user namespace has to be different outside, and it can be different outside and on the inside. Like, not to go too much into details, namespaces are their own beast, so it's worth noting that CRIU needs to restore all these namespaces when it does its restoration, especially for different types of containers like LXC, Docker, containers that run in Kubernetes, and etc. Okay. So the primary component of CRIU that does all this snapshotting and restoring, and actually it's the primary component that is responsible for injecting arbitrary code inside a foreign process. And this code is known as the parasite code. That's a cool name, I think. And the parasite code runs without the standard library, so no glibc, no printf, and you have in like mini architecture of plugins inside this component compile, and there's an std plugin. We can see it here, and technically you bundle these plugins into a library archive, and then your parasite binary, that is your code that implements the parasite, gets this functionality of a parasite. And we'll get a little bit more into how this happens. So this parasite binary is denoted by the file extension .po, a position independent executable, and it's the product that's being injected into the foreign process's address space, like adjacent to the process itself. And one important thing that is like a side thing, but these 4 terms all mean the same thing. I would sometimes juggle them because depending on the context. And so your victim process, where you put your parasite binary, is also sometimes called, especially in CRIU, the dumpy, the trace C when you're in tracer world, like strace, tracer, and trace C, and target is just a generic name that's also used. And yeah, CRIU inject this binary blob, which purpose are to run these so-called, they call them service routines, inside another process as you are another process. And since every you may wonder, like, why would you need to run why don't you do things outside? But there are things like accessing thread local state, some registers, and some syscalls make life easier if they have done as you are the process than if you try to do it outside and then like increase the complexities. And also some functionality is not possible to achieve without running an impersonation of a process. Okay, so the steps towards infection. There are a lot of steps. I mean, I put here 3, but if you would, take a step back, there's like 3 distinct phases. And the first one is just to attach to the process, same as GDB or your VS Code, for example, does when you just attach to a process. We'll get into that too. And then you execute a remote memory map to allocate space for your parasite blob, this executable, and its own stack. And there's an argument area and other things, which we'll show later on another slide where you can see the memory layout. Also, a major thing to mention here is that the tracer, in this case would be CRIU, makes a copy of this shared memory that is just being allocated, and it can write to it, so it can exchange stuff with the parasite directly through memory. There's also a function here, and where you can look it up if you're interested. Yeah, so the first step is to seize the process. So, any of you familiar with ptrace? Right? How many? Okay. strace probably more. So then I don't need to go too much into details, but CRIU uses ptrace to captivate the process, and then it calls another. Ptrace is a syscall that you can get flags, and then it stops the process. So the seize just doesn't alone stop the process; it just obtains ownership in ptrace world of it. And as soon as you send the interrupt, the child should receive a sig trap for which you are waiting in your event loop in CRIU. I mean, CRIU. And that would say that the process stopped, and then you can check its state and see if it's something bad happened to it, or or it's all good. And if it's all good, that means it's ready to be manipulated. And the first step in this manipulation process is actually doing a remote memory map. So ptrace has functions that would allow you to write to the remote processes registers for which you acquired ownership previously. And you can write to registers and memory. And there's a literally syscall ABI for this, which is quite easy to use. And what CRIU, the first thing that it does is it allocates some memory for a syscall. And this requires only 8 bytes. So we're not yet in the parasite. We're allocating for the parasite. And it finds some free VMA. It injects this 8 bytes there and because you can change the register, you can change the program counter, and CRIU sets it to the first ARM instruction SVC to trigger a syscall. And then it resumes the process using ptrace, and the process lands at this SVC line. What that does is that triggers a memory map syscall, because previously it planted all the ABI requirements for that syscall in the registers. And the kernel handles the syscall and then returns here, control back here, and then the next step is Burk, which is an instruction for breakpoint. And if you look in the kernel sources, this eventually triggers back a sig trap to the process. So this is essentially as you did one step in the debugger for just the syscall that you injected. So you just did mmap, stop, get back to CRIU. And then CRIU, I could talk about the Burk instruction, but I think I mentioned most of the things that it does. Then CRIU has allocated some space, and the next step is to create a shared, to share this local shared copy so that CRIU can write to the parasite's memory space. And one of the first steps here, I mentioned previously memory map, but in reality, the preferred way is to use memfd create, which gives you a file handle that doesn't require you to have cap sysadmin capabilities. And it's just the more preferred way. There's a link to a patch that if you want to look at the details. But if that is not possible, it just resorts to an mmap. It could have been any syscall here. Like with that injection technique, you can do whichever syscall. And yeah, so the results by here are that we have shared access to the parasite's memory allocations, and it's visible on both sides. And so now the parasite has its own stack area and other things. And you will see now how the layout looks. At the top is that parasite blob, which is just a position independent executable without glibc. Got tables, some alignments, and the arguments area is when CRIU wants to talk to the parasite, it puts arguments for a certain command or service routine inside the arguments area. But it sends the command through a socket. Now that's a topic on its own, but just so that you know. Then there's some alignment that's required by, I think, the kernel for the sig frame, and sig frame is the secret sauce of CRIU, and I will explain it at some point later. But essentially, it's a data structure that the kernel plants under your stack once your process receives a signal. And yeah, then it has its own main stack and another stack for the different purpose. And what is important here is that the executable has two distinct worlds. like the first one called the bootstrap is an individual per processor, and essentially it just calls an initialization routine in the parasite. So as soon as, but it's required to be similar how the kernel has like a special boot phase. Yeah, here I just wanted to illustrate that you see here that the two injected SVC and Berk that I mentioned. A syscall requires, this syscall requires a string to be allocated somewhere, so I just allocate it underneath. And if you're reversing, you can see it there by no surprise. It just says CRIU MFD for this syscall, and you can see, I think you can see it later in the procfs or something, that this string is there. That's just that. And yeah, here's an example. This is a test that I mostly worked on, but if you were to create your own parasite using binary, you can just include this standard, compels standard library, then make a small switch statement and do something with whatever commands that you do. But you'll see later that CRIU has its own version of this loop. I think I can just quickly show it here on the left and then get back. And you can see that most of the stuff for dumping happens here. So these are all service routines that are inside the process, were compiled into the parasite. Okay, so it's parasite compiling is interesting because there's one step that's kind of awkward. And so first, normally your C file into an object file, and however, you have to use special flags, which you can get using a CLI that's in the repo. And then there's a linker script that's, I think, per architecture as well. Then you make your .pl, which is actually an elf file. And that's the thing that will get loaded in another process's executable area. But the next step is strange, because you take there's a CLI utility, and you take this elf and you turn this elf into a header file. And this header file is actually contains an array of bytes that represent this elf file. That elf file is not big, but essentially in the end you just, with your, I think it's spy.c here, spy.c, you just link your parasite.h and you have embedded your parasite in this byte array, and you're ready to use it upon a victim. Yeah, so I didn't mention that, so we have snapshot and restore, and during dumping, the logic is quite different than during restoring. So the term parasite is often used in dumping, and the term restorer blob is used during restoring, because restore blob doesn't do this. It tries to do everything CRIU tries to do to create as much as possible before it even switches to the process, so that this the restorer code is minimal and fast. Okay, and yeah, so that test that I was showing you, which just incremented and decrements a value, this was key for finding out later. I will add that how the GCC fails. And it's important to note here that as soon as so the decontamination of the parasite at the end of its lifetime happens, so that the parasite calls this function, sigreturn syscall. And what this does is, if you remember the sig frame structure, it uses the kernel looks at your process, looks at your stack and in your sig frame structures, and just resumes the execution of your process, because it's used for signal handling, but CRIU kind of hijacks 50% of it to use it for restoring the process, delegating the responsibility to the kernel, which does it well. And yeah, so that's about it for the intro on CRIU. I hope I didn't confuse too much anybody. And now I will switch to the actual project that I was supposed to implement here. So GCS, maybe you've heard of Shadow Stack on Intel. This is a known feature for quite some time. It is an ARM 9.4-A profile feature, and this is the spec that's not yet on the silicon. So you can't buy a CPU that has this. And this makes it really difficult to implement, because QEMU at that point when the project started didn't have it, and I couldn't find it anywhere. But I'll get to that how I found it. Let me just finish here so what is GCS? It's essentially a hardware security feature that as you, for example, branch out, it stores your value from your link register into the return addresses into a separate memory allocated that is not writable by unless you use a special instruction. And upon returning from a function, it just compares that with the GCS top, and you have integrity in case this protects you against ROP attacks. If anyone knows, if no, it's short for return-oriented programming. And GCS is just an array of return addresses, and this really messed up my brain, because I thought at first that it was just a clone. It was called Shadow Stack. I thought it was just a clone of the regular stack, and it cloned everything, and it grows in the same direction, but it doesn't. And also it doesn't, while debugging, it's good to know that it doesn't, once you pop an address from the stack, it moves its pointer back, and it doesn't really pop the value stays there. So to reduce memory bandwidth, it's not necessary. But this can mess up things if you are debugging and printing stacks and thinking, oh, what are these hexadecimal values all over the place? And so yeah, and there is a special register called GCS PR, stands for pointer, L0 exception level 0 on ARM, that points to the top of this guarded stack, so to call it. And you can find if your hardware supports this by querying the auxiliary vector on Linux by using get aux val. glibc uses the same method to check if your hardware supports GCS, but it doesn't use get aux val because it provides get aux val, it uses something else. Okay, so no hardware, no QEMU. It was a bit disappointing because at that time applying to these projects means you have to research them a lot, so this requires a lot of time, and you have to make a proposal that will pass the mentors, and the competition is quite high. Like, many people are applying. This year was, I think, over 20,000, and they chose only 1,000, something like that, if I'm not mistaken. And yeah, but I was lucky to find this video by a guy called Steve Capras. I think he works at ARM, and at the mini-deb-conf, he presented how they run GCS in a simulator, which is simulator from AMD. It's a clock-accurate simulator, so it's correct, but it's extremely slow. And you can download it. It's called FVP. I forgot what the what this stands for, fast something platform maybe. And this was really good because I saw in the video they could see in the kernel that there's GCS is available. Then because this linked to Arm's repository, Arm the company that has had all these changes in Yocto Linux and BitBake, I think. And then I asked my mentors, but they said that Yocto would not work. And I went on this adventure of trying to cherry pick the patches that they applied to the kernel, to GCC, to glibc, binutils, and GDB. And I almost succeeded. I think I could boot a Debian OS and it showed me GCC is available. I could compile a binary that supports GCC and list the ELF head nodes, and I could see that GCC was there, but it wasn't quite working, and I probably messed up something because it did it involve resolving Git conflicts for the kernel, and definitely wasn't qualified and still on that to do that kind of stuff. But somehow I partially managed it to work, but it was still not good enough to deliver the project. And then someone mentioned, hey, try the new Fedora Rawhide build. And, I tried it and it should be fully patched. And that was it. I could just throw away all the junk that I was trying to do and run this. And GCS shows, it compiles. You run it with GCS. You can see it in the binaries, and you can use glibc tunables to enable it, and it all worked. And end result is that environment is now ready for GCS to be developed. And it was slow, but it was the only thing that worked. There was no other emulation out there. And then the next step was to validate actually that all this patched stuff, because it's recent patches to the kernel that were accepted upstream, that they actually work and that the simulator actually works, because no one really tested that stuff. It's quite new. And this was scary because, any failure here means project dead. And no one wanted that. No one benefited from that. I neither CRIU nor me nor the mentors. And what helped really here was these self-tests in you can find them in the source code of the kernel. And there's 3 of them that I would like to mention. Is that this basic GCS.c, it can teach you a lot about how to enable GCS and how to use the percatel command, and to set regs, get regs, and how to map guarded. I did that. Maybe this is a mistake. Map shadow stack is the name of the syscall. And yeah, you can play around with it, and it also introduces you to how kernel tests work, which is a fun learning experience. The second one was this file, and this stands for GCS, Guarded Control Stack store. So this is the instruction that allows you to write on the Guarded Control Stack if you enable writing on it. And then there is libc.gcs.c. I'm not sure why, but it has tests that contain instruction that allow you to legally jump between different shadow stacks. So this is required in CRIU because during the restore, as I mentioned, it has to be very small. A temporary shadow stack is allocated, and then at the end you have to jump to the original shadow stack that was on the machine where the dump happened. So yeah, this validation was successful, and this was not the end of validation, but it was a big step, because we could confirm that all these things work as expected. Some kernel functions to just to note them that all the GCS stuff happens in them or around them, and that while debugging, bombarding these places with print K was useful. And yeah, so I wouldn't go too much into the details of them, but one is how the map shadow stack syscall works. It basically does an mmap with a special flag on the VMA that says that it's protected, and so on. And also there's some logic on sig return, because and this is important to restoring the process from the signal, and this is the meat of CRIU. So it was really important to look also how does sig return change with GCS in mind, and understand what it expects, because CRIU fabricates this sig frame structure and puts it under the stack. It does so while trying to do it the same way the kernel does. So all the examples how it should look like are there. Yeah. Signal handling in Linux, this is kind of off topic, and we will get back to GCS, but in case, just to repeat what's going on here, and your program running, you get a signal, and the kernel stops your program, pushes this sig frame. Like, these are all registers that were at the time when the signal arrived, and other things. There's a lot of stuff, and then it jumps to the signal handler routine that you registered by sig action. Then as soon as the signal handler finishes the next return from that, like next ret instruction, we'll load the program counter with a planted trampoline, which is actually invoking a syscall sig return. And then it gets back control to the kernel. The kernel looks at here, and your program goes from pause to resume again. I don't know if this makes sense. I tried my best to draw this, but I didn't know anything about this before I started, and it was really confusing for me to what's happening here, because the texts online are here and there. All right. The first set of changes involved, because initially, you maybe remember with the ptrace thing and seizing the process, you need to update the registers of the process. And now, since we have GCS, this also has to be adjusted if GCS is enabled on that process. So why? Because once you're dumping stuff, and maybe you remember at the end of that, there's a sig return. So if something is wrong on the GCS stack, you manipulate it, you have to adjust that so that it passes all that security, bureaucracies. And yeah, again, too much details, some pictures. This is GCS, as you return, goes up, and the top of the GCS is pointed by your GCS PR register. And what the kernel expects on the sig return is these two values, and you can use poke, and so ptrace has poke in peek, read and write to another process to adjust that, so that once it does the sig return, it also validates if the GCS has not been tampered with, and so CRIU makes sure it passes that test. The second set of changes was mostly around restoring the original dumped processes VMA into the newly created process on another machine. And there was lots of challenges here with jumping between stacks, and also it was unclear if, like, there's a syscall called mremap where you take a VMA and you just move it a little bit. It was unclear if you can do this on a shadow stack VMA, but we augmented the kernel tests, tested it, and it worked. And it looks like the information that's actually on lvn.net in an article is incorrect and outdated. You can actually do this. There was a patch to prevent this, but it was never accepted, so it stayed somehow mysterious. And yeah, so to restore in the newly created process this old dumped shadow stack VMA, you have to write to this stack, and this can only be done by the GCS str 8 bytes at a time. And yeah, this leads us to thinking what changes in the kernel might be needed to not having to do this, like being able to just point another VMA to be a new shadow stack VMA or something like that. And yeah, it's a similar process like during the dump, except that one difference is that you're not just preparing it for a SIG return, also for a jump to another stack from your temporary stack to the original stack. And you can see in the kernel code that you have to do some bitwise masking stuff, and that would make the jump valid. And also the documentation on ARM for jumping expects that, but it's not well explained in the text what is expected. And yeah, so once you jump into the restored process as a shadow stack, all done, all good, and this is happy days after that. And so for debugging, CRIU, not the kernel, it was really useful to just dump the hell a lot of this SIG frame structure to understand first, because this was all new concepts for me. I didn't really know much about it. And okay, critical PR debugs at some points in the parasite, outside of the parasite. It would have been useful to have some kind of clear distinction where things are happening. And there is something in the logs, but I don't know. I'm abstractly thinking something different might be more helpful. And dumping proc maps and S maps, really useful, but S maps is huge, so you have to adjust the output a little bit, otherwise you just get noise. Content of the shadow stack, and I just wrote some helper functions that would do like a nice ASCII thing and put actually an emoji where the GCS pointer is, because then when I search the logs, I just search for the emoji. And yeah, ChatGPT is not always wrong. Okay, top of the stack, also to indicate this token stuff, because if you make a mistake of one slot, it's really easy to like lose your mind. And what was helpful really was to turn off randomization, because you're working with predictable addresses, and as you do it 1 month, 2nd month, then you start to remember these addresses, like you can tell the hex from your head. So that's nice, but also in the end, when you're testing, you should try both, because this is how we've actually found the bug. There was a bug that was not present, or that was present only when randomization was off. And yeah, kernel debugging, I just used print K because for me it's even patching the kernel was locally, just not upstream. That's harder. Was you know, like a monster, but you just figure it out. You find places where you want to print. I defined some macros that can print based on which process it is, task that it is related to, and then I can just filter it out. But there are much better ways to do kernel debugging, and I'm currently exploring ftrace and other things to do more kind of dynamic stuff, but this topic on its own. And yeah, we're near the end. Some links, if you're interested. I'm building a blog, so this is a previous section, and there is a small playground for GCS tests, kernel tests, to check this mremap stuff. And there is a GCS box, which is how to run all this simulator stuff and build the environment so that you can play around with GCS. I doubt anyone has enthusiasm for it, but in case you want, yeah. Some links to the patches, articles, and I would not be possible without these 3 mentors. So the best thing about this project was having people who really know CRIU and who are really experienced at the systems programming. And additionally, I want to thank Dennis Luna, which yesterday helped me a little bit with the slides. He works at Virtuoso. So yeah, that's it. I'm done. I guess questions, but I cannot guarantee I can answer them because for CRIU I'm a beginner, but maybe I can try, or yeah, or maybe you can send me an email and you'll get your answer once I do the research.
I didn't get. Could you please explain it? Why do we, during the restoration procedure, why do we need to inject the parasite if we already kind of dumped all the memory, and I assume including the parasite?
I will know exactly, but I believe it has something to do with some calls have to be run as the process itself, like I don't know, clone or something. You know, I don't know exactly to answer, but yeah, it's a thing I can find out and learn more.
Thanks.
So do you intend on maintaining
Absolutely.
stock?
Absolutely, I love it, and you know, no one's paying you to do it, and the people there are great. For me, it was the mentors, having people that know so much and that can guide you, and like you're on, you know, like you're like a kid on small bicycle with helper wheels, and eventually you start to get stuff, and you know you can get better. So definitely, I already am. I'm already looking for new stuff that I can work there, and even presenting here is kind of some contribution. Okay. No, it's perfectly legal. So there are no known, not to my mind, but there are people who might know like how you can. It's a tool that looks powerful that maybe in the wrong hands, someone has malicious ways of using it, and the OS doesn't stop you. But again, I don't know that much about CRIU. Maybe in the past there was some stuff. That's why the code base is huge. It's really complex and a piece of art, I would say. Yeah.
Well, you were talking about the GSIU. Let's say, for an example, that a process has already initialized connection, socket connection. That's another process, and that another process has a part of the program state that was made after the initialization of the socket connection. How would that part of this program state be restored, given that it is not inside that process? And if the process starts to run again, it will have to initialize the socket connection again and repeat the process that is already done.
I guess it would break there. I mean, maybe there are some mechanisms that I'm not aware of, but I know that it does restore it, but maybe this depends on the more of a stateless kind of designer, like outside of CRIU. So maybe there's something, but I don't know.
It'd be great if there was a specific signal handler for when the process is brought up again from the and
To repeat.
state to be initialized again. And another question regarding GS,
DCS.
it basically duplicates the ordinary stack.
No, it just stores the return addresses of from where you branched out. Yeah, so this is what I thought the same. This is why the first few weeks I had like a mind confusion about where all these values coming from. Okay.
Sorry, maybe I have missed it. So initially we have this setup with the parasite object to inject, like to basically do context issue, like the stackful coordinates, that stuff like this. And we already could do it before GCS.
Yes,
Yeah.
but it would break with GCS actually if GCS is enabled on the process, and you don't know because people implement CRIU in run C, for example, and there's so many container runtimes that it has to work for the new hardware features.
So everything like exclusively cooperative. Like we have our image with our process, which we specifically configure for the way we're gonna dump and restore.
Yeah, there are. If you're referring to the dumped images,
Like the whole process, because what exactly we want to like store and restore later, like we need to cooperate our like deployment of application and something.
no, like you just have to run. Like and this is
We can use an arbitrary system. You
Yeah.
just need to know.
you just call dump and restore.
Ah,
But this is implemented, for example, outside. You have, I think, Docker also has dump and restore, and there's run C and Podman. I don't know, like you would see, but underneath it's CRIU or linked or maybe as a separate binary, depending on the implementation. But yeah.
Do you have any advice for anybody looking to apply for Google Summer of Code?
Yeah, it's a good question actually, and I have only if you have the time. That's my advice. And if you don't, it's gonna get difficult because you need to bite. You know, like if you want a more advanced project, like you can apply for something. I applied one more and I got accepted there, but the algorithm in the end, you don't choose the final one. That you have to choose one. It was NetBSD and something like changing boot UEFI params, and this was there's 3 levels of difficulties. Easy, medium, hard. I don't know. And easy is the shortest one. It takes the shortest. It's the least amount of perceived work, and yeah. So if you don't have time, you still can, I think, with the easy one. But if you want a hard one, I think you should, consider it almost like a job. Yeah.
Thank you.
pursue.